For nearly a century, we've been told a simple story about the beginning of everything. The universe began in an extremely hot, dense state. It expanded. Space itself stretched. Galaxies eventually formed. Stars ignited. Planets appeared. And billions of years later, here we are. It sounds almost complete. But then astronomers started looking deeper into the ancient universe, and something strange happened. The farther scientists looked into the past, the more they began finding galaxies that seemed surprisingly mature for their age. Some appeared brighter, more massive, or more developed than astronomers expected from such an early stage of cosmic history. Then came observations from one of humanity's most powerful space telescopes, the James Webb Space Telescope. Instead of simply confirming everything scientists expected to see, Webb opened a window into an era of the universe we had never been able to observe in this detail. And what it found forced astronomers to reconsider some of their assumptions. But here's where the story gets interesting. Big Bang theory itself has not simply been destroyed. The cosmic microwave background still exists. The universe is still expanding, and multiple independent observations continue to support the idea that our universe evolved from an extremely hot, dense early state. So what exactly changed? The answer may be more fascinating than the headline, because scientists aren't necessarily rewriting the beginning of the universe. They may be rewriting what happened during its earliest chapters. And if those first few 100 million years unfolded differently than we imagined, then one of the biggest mysteries in science becomes even bigger. How did the universe become structured so quickly? Today we're going back to the beginning, not just to ask how the universe started, but to discover what the newest observations are revealing about the universe when it was still almost unimaginably young. Part 1. The old picture of the universe. For most of human history, people didn't even know whether the universe had a beginning. The night sky looked eternal, stars appeared fixed. The Milky Way seemed like a permanent structure hanging above Earth. Then, during the 20th century, astronomy changed everything. Scientists discovered that distant galaxies weren't simply sitting still. Their light was shifted toward the red end of the spectrum, a phenomenon known as redshift. And one of the major interpretations was extraordinary. Space itself was expanding. Imagine drawing dots on the surface of a balloon. As the balloon expands, every dot moves farther away from every other dot. Now imagine reversing that expansion. The galaxies would appear to move closer together. Continue the thought backward far enough, and the universe reaches an incredibly hot and dense early state. This became the foundation of what we now call the Big Bang model. But there's an important misunderstanding. The Big Bang wasn't an explosion that happened at one particular location in empty space. There wasn't necessarily a giant bomb sitting somewhere in the universe. Instead, the model describes the early universe itself expanding. And that distinction matters, because when we look farther away, we're also looking farther back in time. Light doesn't travel instantaneously. The sunlight reaching your eyes took about 8 minutes to cross the distance from the sun to Earth. When astronomers observe a galaxy millions or billions of light years away, they're seeing that galaxy as it existed millions or billions of years ago. In other words, telescopes are also time machines, and the farther they can see, the closer they can get to the universe's earliest observable history. For decades, scientists built increasingly sophisticated models describing how the young universe should evolve. Tiny fluctuations in the early universe would grow under gravity. Gas would collect. The first stars would ignite. Stars would gather into galaxies. Galaxies would merge. Black holes would grow. And eventually, enormous cosmic structures would emerge. The basic framework worked remarkably well, but there was always one enormous limitation. We couldn't directly observe the earliest galaxies in enough detail until recently. Part 2. Enter the James Webb Space Telescope. In December 2021, something extraordinary happened. The James Webb Space Telescope launched into space. Unlike ordinary telescopes that primarily observe visible light, Webb was designed to observe infrared wavelengths. That capability is extremely important when studying the early universe. As the universe expands, light traveling through it becomes stretched. Ancient light that originally existed at shorter wavelengths can arrive at Earth shifted into the infrared. Webb was built to detect that faint ancient glow. And suddenly, astronomers could investigate galaxies from an era far closer to the beginning of cosmic history than ever before. The first results were breathtaking. Webb detected extremely distant galaxies. Some existed only a few 100 million years after the universe's early expansion began, and some appeared unexpectedly bright. That created a scientific puzzle. If a galaxy existed when the universe was extremely young, how did it already contain so many stars? How did those stars form so quickly? How did the galaxy assemble? And how did some of its central black holes become so massive? At first glance, it looked like the universe had broken the rules. But science doesn't work by stopping at the surprising observation. Astronomers immediately began asking another question. Were our expectations wrong, or were we misinterpreting what Webb was seeing? That distinction is crucial. Early observations can be misleading. A galaxy can appear brighter because of its star formation history. Distance estimates can change. Dust can affect observations. Mass estimates can be revised. And some objects initially thought to be enormous can turn out to be less extreme after additional analysis. So rather than proving that the Big Bang was wrong, Webb forced scientists to examine the details of how galaxies formed. And that's where the real mystery begins. Part 3. The galaxies that seemed too mature. Picture the universe only a few 100 million years after its beginning. Compared with today's universe, it was incredibly young. There were no humans, no Earth, no Sun, no Milky Way as we know it. Yet Webb showed astronomers galaxies already shining across enormous cosmic distances. Some appeared much brighter than expected. This raised a fascinating possibility. Maybe the earliest galaxies were capable of forming stars much more efficiently than our older models predicted. Maybe the first generations of stars behaved differently. Maybe galaxies accumulated mass faster. Maybe black holes grew through processes we don't completely understand. Or perhaps some of the initial observations simply represented unusual galaxies rather than the average galaxy of the early universe. And there's another important possibility. Our models of galaxy formation may have been too simplified. The Big Bang model tells us about the evolution of the universe on the largest scales. But it doesn't automatically tell us every detail of how the first galaxies formed. Think of it like knowing the starting conditions of a giant simulation. You can understand the overall rules without knowing exactly what every individual galaxy will look like. That's why the Webb observations are so valuable. They're giving scientists actual data from an era that was previously dominated by theoretical predictions. And sometimes the universe doesn't behave exactly like our first computer simulations predicted. That's not failure. That's science working. Because when observations disagree with expectations, scientists don't get to simply choose the observation they prefer. They have to investigate. And some of those investigations have produced another surprising clue. Part 4. The black hole problem. Galaxies weren't the only thing surprising astronomers. Webb also detected evidence of massive black holes in the early universe. And that creates an enormous question. Black holes don't simply appear at enormous sizes. According to conventional models, they need some kind of seed. That seed could begin as the remnant of a massive early star. Then gravity pulls in surrounding matter. Over time, the black hole grows. But the universe's early timeline creates a problem. If some black holes were already extremely massive when the universe was young, they didn't have an enormous amount of time to grow. So how did they become so large? There are several possibilities. Perhaps the earliest black holes were born from unusually massive stars. Perhaps some black holes formed directly from collapsing clouds of gas. Perhaps they grew incredibly efficiently. Or perhaps multiple mechanisms worked together. Scientists are actively studying these possibilities. And this is where the headline becomes much more interesting. The Big Bang model doesn't necessarily need to be thrown away. Instead, our understanding of what happened after the earliest expansion may need major refinement. The universe may have been capable of producing its first stars, galaxies, and black holes faster than older models suggested. But there's an even deeper mystery. Because Webb isn't only looking at individual galaxies, it's helping scientists reconstruct an entire cosmic timeline. And when you move backward far enough, you reach something even stranger. Part 5. The afterglow of creation. Long before stars existed, the universe was filled with an incredibly hot plasma. Eventually, it expanded and cooled enough for atoms to form. And when that happened, light was finally able to travel freely through space. That ancient radiation is still traveling through the universe today. Scientists call it the cosmic microwave background, or CMB. It is one of the most important pieces of evidence supporting our modern picture of cosmic evolution. The CMB isn't an image of the Big Bang itself. Instead, it's a snapshot of the universe when it was roughly 380,000 years old. That's unbelievably young compared with today's universe. And the CMB contains tiny variations in temperature and density. Those tiny differences matter enormously, because over billions of years, gravity amplified them. Regions with slightly more matter pulled in more matter. Structures grew, stars formed, galaxies assembled, and eventually, the enormous cosmic web emerged. So when scientists compare the CMB with the modern universe, they're essentially comparing the universe's childhood with its adulthood. And remarkably, the overall picture fits together, but Webb is now filling in the missing pages between those two eras. The CMB shows us the young universe. Modern telescopes show us the mature universe. Webb is helping us see what happened in between, and that's where some of the biggest surprises are appearing. Part 6. So did the Big Bang theory break? Here's the twist. No, at least not in the simple way viral headlines sometimes suggest. Scientists haven't suddenly discovered that the universe never had a hot, dense beginning. They haven't found a telescope image proving that the Big Bang was an explosion in empty space. And they haven't replaced the entire framework of modern cosmology overnight. Instead, they're discovering that the early universe may have been more complicated than our previous models suggested. This is a crucial difference. Imagine discovering that a historical civilization built enormous cities much earlier than archaeologists expected. That wouldn't necessarily mean the civilization never existed. It would mean our understanding of its development was incomplete. That's similar to what is happening in cosmology. The broad framework remains extraordinarily powerful, but the details are being challenged. How quickly did the first stars form? How efficiently did galaxies convert gas into stars? How quickly could black holes grow? How did the earliest galaxies organize themselves? And what physical processes dominated those first few 100 million years? These aren't small questions. They reach directly into one of the greatest scientific mysteries imaginable, because the early universe wasn't merely the beginning of galaxies. It was the beginning of the cosmic environment that eventually made everything we know possible. Part 7. The bigger meaning. There is something almost philosophical about this discovery. For thousands of years, humans looked upward and imagined the universe as something permanent. Then science revealed that the cosmos changes. Stars are born, stars die, galaxies collide, black holes grow, and even space itself expands. Now we're discovering that the earliest universe may have been more dynamic than we imagined. The first galaxies may have formed rapidly. The first black holes may have grown through unfamiliar pathways. And structures may have emerged under conditions we are still struggling to reconstruct. But there's a deeper lesson here. Science doesn't advance because scientists already know everything. It advances because scientists are willing to say, our model predicted this. But the universe showed us something else. That's one of the most powerful ideas in science. A telescope doesn't care what humans expect to see. A galaxy doesn't change its behavior because our textbook says it shouldn't exist yet. Nature simply does what nature does, and our job is to catch up. That's why the James Webb Space Telescope is so important. Its greatest achievement may not be giving us beautiful pictures of distant galaxies. Its greatest achievement may be forcing us to ask better questions. Because every time we look deeper into the universe, we discover that the story is bigger than we thought. Final twist. We may still be missing the first chapter. And here's the part that should leave you thinking. James Webb can see incredibly far back in time, but it still cannot see the exact beginning of the universe. There is a barrier. Before the universe became transparent, light couldn't travel freely through space. So even the most powerful telescope cannot simply look through that early cosmic fog and photograph the beginning. We're still missing the first chapter. We have indirect evidence. We have mathematical models. We have the cosmic microwave background. We have observations of ancient galaxies. And we have increasingly powerful simulations. But the deepest question remains: what actually happened at the earliest moment we can meaningfully describe? Was there a period before the hot, dense universe? What caused cosmic inflation, if inflation occurred? Why does the universe contain more matter than antimatter? Why do the laws of physics have the values they do? And how did tiny primordial fluctuations eventually become galaxies, stars, planets, and eventually conscious observers capable of looking back at the universe and asking where it came from? We don't have all the answers. And perhaps that's exactly why this story matters, because the latest discoveries haven't necessarily destroyed our picture of the universe. They've done something more exciting. They've shown us that our picture is still incomplete. The universe may have been stranger, faster, and more chaotic in its infancy than we ever imagined. And somewhere beyond the oldest light we can currently detect, the first chapter of cosmic history is still waiting. We just haven't learned how to read it yet.